Hi guys, this is Kate, and this is the third video for week 2 of Math 23B. Let's start off with some uses of Fubini's theorem. Note that sometimes you encounter an integral that you can't really do in the order that it's first expressed in. For instance, this example. We're taking a double integral, expressing it as an iterated integral, and we've decided to express it as an integral with respect to x first and then with respect to y. And the function that we're trying to integrate with respect to x is 4 times e to the x to the 4th power. And already, I just look at this and I'm stuck. What is the antiderivative of 4 times e to the x to the 4th power? I mean, I try to do a little like reverse chain rule, but everything that I think ends up being an antiderivative isn't actually an antiderivative, because when I end up taking the derivative of the antiderivative, I don't get the original function itself. That's usually the way I check whether I've gotten the antiderivative correct or not. So I'm totally stuck, and at first you might start to panic, but really, this is just an invitation for you to use Fubini's theorem. And problems like these show up in like every single multivariable calculus class that exists. And here's what you have to do. You need to switch the order of integration. Just like I discussed on the previous page, it's really important to be able to go from a picture of a region to the bounds in either direction and back. So this is one of those instances where I've got to go from the bound to the picture of the region. So let's take a look at it. First thing that we can deduce from these two bounds right here are that x is going to be greater than or equal to the lower bound, the cube root of y, and less than or equal to the upper bound, 2. So let's write that down explicitly. Then on top of that, we take a look at y, and we see that y has to be greater than or equal to 0 and less than or equal to 8. Those are our bounds for x and y. So let's use this blank space right here and give yourselves an opportunity to try to sketch this region. Put the video on pause, try it out, and then return for the answer. Okay, let's take a look. You think you're ready? The first thing that we note is that as we're moving in an x-wardly direction, the first curve that we're going to intersect is the cube root of y, which I've drawn on here. And then the next thing we're going to hit is x equals 2. Then when we project this region's shadow onto the y-axis. Now you might be thinking, wait, what is the region? Remember, the x-coordinate has to be greater than the cube root of y and less than 2, which means that it is everything inside here. So that's our region. Now when we project it onto the y-axis, we're looking at the interval from 0 to 8. And that makes sense, because when we plug in 2 for x right in here, we know that y has to be equal to 8. All right, so we've basically given ourselves the region. We can picture it. Now we want to try and swap the order in which we're describing this. We want to start with y bounds, which means that we want to head in a y-wardly direction. The first thing that we're going to hit as we enter this region is this right here, y equals 0. Then as we keep heading north or in a y-wardly direction, the last thing we're going to hit as we exit the region is this, x equals the cube root of y. But remember that we can't use y when we're describing y bounds. We want to describe y bounds as functions of x. So of course, we can algebraically rearrange this and express y as a function of x, which is just y equals x cubed. Those are our y bounds. I'll even write them down as inequalities up here too. Then we want to take our region, and instead of projecting onto the y-axis, we now want to project onto the x-axis to get the appropriate interval bounds for our x integrand. So when we take this entire region and project it, see what its shadow is, on the x-axis, we note that it's along here, which is from 0 to 2 in terms of x. Now, lo and behold, what's fantastic about this is we can absolutely take the antiderivative of 4 times e to the x to the 4th power with respect to y. Because remember, when we're taking the antiderivative of something with respect to a particular variable, it's similar to taking the partial derivative of something with respect to a particular variable. You pretend all the other variables are constant. So the fact that we're taking the antiderivative with respect to y means we treat x as constant. So this is the same thing as just finding the antiderivative of like 5 with respect to y, which would be 5y. Or the following. This becomes 4y times e to the x to the 4th. when we're doing that inside integral. Now, you may be wondering, what exactly is so great about that? Well, when you plug in x cubed, you end up with 4x cubed times e to the x to the fourth, and then minus 4 times 0 times e to the x to the fourth, because we're plugging in x cubed and 0, the two endpoints, for y here. And here, what's left is a nice integral that can just be done by regular old u substitution, right? X to the fourth is our u, then 4x cubed is our du, which ends up being right here. I'm not going to finish this out because it's just a straightforward u substitution integral, but you can see how we started out with a particular integration order where we couldn't move at all. We had no idea what the antiderivative with respect to x was, and instead of just giving up and throwing our hands in the air, we decided, hey, let's figure out what this region is, let's draw it up here, let's swap the order of integration, describe it in a different order, and see if that helps. And there's always, always a problem on the quiz or a problem on the final exam that hinges on your ability to alleviate a problem like this by swapping the bounds of integration. As you can tell, it's super important that you're able not just to go from the picture to the bounds of the integral, but in order to even begin this problem, you needed to go from the bounds to the picture and back to a different set of bounds. So very, very difficult to accomplish this successfully without using that intermediate picture, because how would you necessarily have been able to figure out exactly what the other order of bounds would be? I don't know. But make sure that you're clear on using pictures to figure out what everything looks like. The other pro tip I would say is that there's always a student or students on the exam that go a little bit too fast and they don't pay attention to this particular relationship, that y has to be between 0, greater than 0, less than x cubed, or that x has to be greater than the cube root of y and less than 2. And so instead of shading in this part and thinking that that's your region of integration, they think it's this part, this is the region of integration. And you'll just get a totally different answer because it's a totally different region. But it always stinks to lose points on something as small as that. So make sure you're going slowly, carefully, making sure you're clear on what the region of integration is. And it's always about how do you bound x and y. That will tell you where your region is. Last but not least in this particular bullet, we didn't actually prove last term that for a twice differentiable function, they're mixed partials, or what you get when you take the partial with respect to y and then with respect to x of a function versus what you get when you take the partial with respect to x and then with respect to y of a function, that those are equal. And as long as we're willing to assume that the partial derivatives are continuous, we can construct a really easy proof of the fact that mixed partials are equal using Fubini's theorem. And this is going to be your proof 15.2. And the way it's going to go is we're going to start off by showing that the integral of the difference of the mixed partials over any square must be equal to 0. Once we've demonstrated that the integral of the difference is equal to 0, we're then going to use continuity, that if this integral is equal to 0, that will only happen if this function itself is equal to 0. Which means that if these two things their difference is equal to 0, that means that they're equal. Hence, the mixed partials are equal. So keep an eye out for that this week. Last but not least, a couple tiny clarifications about Fubini's theorem. A lot of people get really pumped about Fubini's theorem, and they think that it means it's always okay to reverse the order of integration in an iterated integral. Well, what if we look at this double integral? Note that we have bounds 0 to 1 in the x direction and 0 to infinity in the y direction, and then we swap that order of integration down here. What's interesting is that this order of integration evaluates to 0, this order of integration evaluates to 1, and you might be thinking, Fubini, you have failed me. But in fact, he has not. Fubini's theorem only applies when the given iterated integral represents a valid double integral, as in this original double integral can be calculated like dyadic cube style, with upper and lower sums approaching the same value as the level of dyadic division goes to infinity. That kind of double integral exists. So remember that that means that the function must be bounded for it to be Riemann integrable in that style, and must have bounded support. And here we are dealing with an unbounded interval. We have this infinite limit when we're dealing with y. And so this isn't a Riemann integral at all. So we can't apply Fubini's theorem. We can't just like swap and say, oh, we can always reverse the order. The original double integral must be Riemann integrable itself. Let's take a look at another example. Another thing to emphasize is that Fubini's theorem says only that if you can evaluate a multiple integral as an integrated integral using two different orders of integration, you will get the same answer using either order. Meaning that only if you're able to integrate it in either order will you get the same value. Here's an example of an integrable function of two variables that can be evaluated by iterated integrals in one order but not in the other. So here's the domain. This is the unit square. What's going on with this function that it's equal to 1 inside the square as well as 3 of the boundaries, the top, the left, and the bottom boundary. And it's equal to 0 outside the square, and along this side right here, we have a bit of an issue. Well, all along this side, x is equal to 1. When y is rational, the function is equal to 1, and when y is irrational, the function is equal to 0. You already have experimented with a function like this before. Now let's see what happens. If we integrate first over x, there's actually no problem. In that particular case, our innermost integral is going to look like this. Is the function f integrated from 0 to 1 integrated over x? What's interesting is like, yeah, when x equals 1, the function goes like a little haywire along here. But the actual discontinuity there, when y is like irrational or rational, it's either 0 or 1, respectively, that doesn't matter because it's only happening when x equals 1, and that is a set of volume 0. So the actual function value at x equals 1 doesn't matter. We're able to compute this. This would be equal to 1. Then we'd go ahead and integrate 1 over y from 0 to 1, and then we'd get 1 again. So that works. When we integrate with respect to x first, that's excellent. But when we integrate with respect to y, that is an issue. If we integrate with respect to y first, we have this. So when we're integrating with respect to y first, this is our innermost integral. And honestly, for x between 0 and 1, not inclusive of 1, this function is totally fine. But when x equals 1, we have a really unique problem. This guy right here does not exist. Why do I know that? We've actually already seen this integral. This one right here. Yeah, last week we talked about a special function that was defined on the interval from 0 to 1. It was a univariate function that was equal to 1 for rational x and 0 otherwise, and we asked if it was integrable. We found that no matter how finely you slice those dyadic cubes, you will always have a rational and an irrational number in any dyadic cube on that interval, no matter how small it is. And so the oscillation's never going to go to 0. So the same problem is happening here when x is equal to 1. The function is not integrable when x is equal to 1. And so we end up with this situation where if we try to integrate with respect to y first, there's just no way. The integral does not exist if we integrate with respect to y. But if we swap the order, we integrate with respect to x first, the integral does exist and we're actually able to compute it. This example is a little finicky of an example, but it's going to be a topic of discussion this week in class. Because no, we can't compute it in this order. This guy right here does not exist. DNE. But swapping the order does allow us to compute this integral. If we do x first and have this be our inside integral, great, no problem. We can then take this and integrate it from 0 to 1 in terms of y, no sweat. But this right here, this guy does not exist when x equals 1. And that's a problem. But of course, you might suspect that since this fumble, this interference, occurs on a set of volume 0, the value that we get when we are able to compute the integral is the value of the integral itself, and we will go through step by step why that is in this case. So, lots to look forward to this week. As always, if you have any questions at all, please don't hesitate to email.